Hi, this is Jessica Kalinowski, and this is week 2 of the readings for using information effectively in philosophy. The reading that we had to do this week was on chaos theory and small world networks. So it gets pretty heavy at times, but hopefully I can help explain it a little bit better. One of the main facets of chaos theory that we learned basically started with Edward Lorenz's equations in 1963. He created 3 equations that generated chaos, seemingly random, unpredictable behavior, governed by non-random deterministic laws. So basically nobody could solve them. However, the ways to solve them were easily available. And another is that systems are ruled by chaos, are mostly nonlinear, in that the whole is not equal to the sum of the parts. So it's pretty important that that the systems that are ruled by chaos are nonlinear, because most systems only behave linearly when they are close to equilibrium. And that doesn't happen very often. So most of the time, most systems are nonlinear. So more attention needs to be paid to that. Nonlinear problems and nonlinear systems are also more complex than linear ones. And they often find that simple nonlinear problems can show complicated behavior that is unprecedented. And my example of this is with ants. Ants seem pretty simple animals, pretty simple creatures. However, they have recently discovered that they use bidirectional feedback teaching, which is just a fancy phrase for they actually teach each other how to do something. And this is important because there's a difference between teaching and copying. And most animals, when they teach their young, the young are just copying off of what the older one does. However, with the bidirectional feedback teaching, the teacher or the adult changes his behavior according to what the pupil's learning curve basically is. So they're actually teaching them with feedback from the pupil. So it's the only recorded or known use of bidirectional feedback other than humans in the universe, basically. So it's pretty huge. And then the other main feature of chaos theory is the butterfly effect, and we all pretty much know what that is, but we don't really understand it. It was originally coined by Lorenz, once again, in 1979, by a paper that he wrote called Predictability. Does the flap of a butterfly's wing in Brazil set off a tornado in Texas? Basically saying that in a chaotic system, there's a direct quote from our reading saying that in a chaotic system, small disturbances grow exponentially fast, rendering long-term prediction impossible. So basically saying that a system can be predicted in the short term, but not in the long term. And this is because of the deterministic laws and the unpredictability of the butterfly effect. So the laws that govern the chaotic system are deterministic, basically saying that you can use the current state determines the future state uniquely. So based on the laws, you can figure out on the short term what will happen in the future. However, because of the butterfly effect, which is basically an insignificant event can trigger a disproportionate chain reaction, you cannot predict in the long term. So my example of the butterfly effect is a hypothetical. So basically, if a herd of elephants in the Serengeti during the dry season is marching towards a watering hole, all the watering hole knowledge, all of them are stored in the brains of the matriarch and the elder females in the herd. And if the one watering hole they go to is dried up, they usually go to a different one. However, the distance between the one they chose is very large from the next one. And what if the matriarch dies en route? Then they get lost. They don't find the next watering hole, which means a lot more can die, and then the lion population can explode because they have all of this fresh, huge amounts of meat. And then the spike in lions, once they run out of the elephant, they turn towards zebra. And they pick off more zebra populations than they would have been able to with a smaller lion population. So it could lead to the extinction of the zebra. Now, that is a very unlikely situation, but it's just one example of the butterfly effect. Okay, and then now on to small world networks. Basically, small world networks believe or show that everyone is connected by a short chain of intermediaries, and it is a unifying feature of diverse networks found in nature and technology. In the very early workings of small world networks, we learned of coordinated behaviors, which is a pair of identical rhythms in sync. So basically, crickets chirping in unison, or fireflies blinking in unison, basic stuff like that. And chaotic systems can be put into networks. However, the wiring of it matters because the structure always affects the function. And my example of this is basically in any ecosystem, you have to have what we like to call a pyramid shape of species. So you need to have at the base, you need to have stuff that the herbivores eat, like grasses and such. And then as you go up the pyramid, the number of species and the size of the populations of those species dwindles. So at the very top are the carnivores, and the highest on the biggest and largest on the ring of carnivores. So the ones that eat the biggest herbivores, and they have to have the smallest amount of population because they eat a lot. And if this pyramid is not, if it's off balance, or if there's more carnivores than herbivores, then the ecosystem will collapse because there's no way of keeping that ecosystem going. And then with networks, there are two statistics used to develop their structure. There's the average path length, which reflects the global structure. It depends on the entire network, and it depends on how the entire network is connected. And the other one is clustering, which reflects the local structure and only affected by the interconnectedness of local neighborhoods. So basically, if it's like a circle, a ring of clusters of of dots, I guess you can say. And then randomness or chaos in the system drastically changes the statistics. A small amount of chaos plummets average path length, but the clusters don't change. Also, rewired networks manage to be both small in length and highly clustered simultaneously. And my example for this goes back to the ant colonies. Now, even though there's like millions and millions and millions of ants, they're all clustered, they're all grouped into one small area in the colony, the hive. And within this hive, there's clusters of different types of ants that live together. So that's highly clustered in a small space. And then the rewiring caused by chaos allows for shortcuts between clusters in this group. So, the average path length is shorter, and shortcuts between clusters that are spread very far apart allows faster communication channels as a whole that enable mutual influence to spread quickly throughout the population. So basically, the unite is one if there's a unite is one faster than there would be without the shortcuts. And going back to the ant colonies, even though there's millions and millions of them, they are always coordinated and move systematically in a very highly organized way. And one of the main reasons why they're able to do this so effectively is because they use hormones and pheromones for just about anything. So if they want the colony to attack, they send out a pheromone that travels throughout the space of the colony and through the air faster than the ants if they were moving one by one. So they can detect the pheromones faster than if one of them touched them and was like, hey, we need to attack. They attack the pheromones allow them to sense that they need to attack in milliseconds rather than seconds. So they're highly organized and they're able to communicate much faster than without the chaos in the system. So that's all I have for these two. So hopefully I helped explain a little bit better. And if not, you can always ask me questions and leave some comments. Thank you.